this video, Adam Chernick from Shop Architects shows us how he used InstaLOD to automate their entire pipeline, going from large BIM datasets with tens of thousands of parts and millions of polygons to a real-time ready scene that runs smoothly on a tablet. Adam walks us through this process step by step, showing us how he utilizes InstaLOD's scene import rules to prepare a BIM model with materials, specific tessellation settings, and finally optimizes everything to a usable, low amount of polygons. In a typical PLM system, files are updated and changed weekly, if not daily, which creates a huge amount of continuous work in keeping the 3D files updated. With InstaLOD's scene import rules, however, artists and engineers no longer have to manually prepare or update the meshes, saving hours of work for every update made to the CAD files. Entire processes from the CAD tessellation, material assignments, and hierarchy organization across UV generation and polygon reductions can be automated with an easy-to-establish set of rules. With this kind of automation, these scene import rules become a crucial step for the full automation of any PLM, BIM, or data regeneration pipeline. Once Adam has set up a profile for a single floor, he utilizes InstaLOD Pipeline to automate this process across the entire building, saving him days of work. I hope you enjoy his demonstration.
Hello. My name is Adam Chernick, and I work at Shop Architects doing research and development for virtual and augmented reality. And today I'm going to walk you through a little bit about how we use InstaLOD in our workflows here at Shop Architects and how their mesh optimization is crucial for some of our AR and VR workflows. So what we're going to do today is we are going to pull some geometry from one of our projects from a few different authoring tools from both Revit and Rhinoceros. And then we're going to bring them into InstaLOD, we're going to optimize them, and then we're going to actually use that InstaLOD profile to optimize many meshes. So we're going to show you how we can, scale this to a project that, has 80 floors, for example. So we're going to walk you through all of these processes and then build an augmented reality application for mobile. And go from there. We are in Revit here, and we have our project. As you can see, we have broken out this project into floor sections. These floor sections we are going to export out so that we can optimize them in InstaLOD and then bring them into our game engine. So in order to do that, we are just going to file export. Within export of Revit, we have a few different export options. We have IFC and FBX, as well as CAD DWG formats. We are going to pick DWG today. Both FBX and IFC are beneficial for different reasons. Both of them can be used within InstaLOD, but for this specific workflow that I'm describing today, I've found that DWG is going to be our best bet just in terms of retaining hierarchy and naming conventions so that we can automate a lot of these tasks within InstaLOD. In Rhino really quick, we took our DWG export from Revit. You can see that all of these layers are very nicely broken up, and we are just going to export this to an FBX. So now that we have converted our DWG out of Revit to an FBX, we are going to import it into InstaLOD Studio and build an optimization profile. And so I am actually going to open up a recent profile that I have created and walk you through this profile and my reasoning behind what we have built for this specific import. And then after this profile has been created, we can then use it within InstaLOD pipeline to run over multiple models. And then we can get the same result from one profile over many sections of this building. So looking at this model now within InstaLOD Studio XL, we can notice over here in the outliner that our hierarchy is the same as it was within Rhino when we exported the FBX, which is great. A few things to notice is down at the bottom here, we have some cameras that came through with the FBX out of Rhino. And so what we are going to do here is we're going to set up some scene import rules, which is just to say that when we are, the first thing that's going to happen to this model when we import it or when we run this profile on top of a model is it's going to run these scene import rules before it runs these mesh operations. And so the first rule is just going to delete out those cameras. All we're doing here is we're setting an attribute. It's looking for a specific name of an element in the hierarchy. It's looking for these cameras here. And so all that we're going to do here is insert those selected elements within this hierarchy. That is going to grab those specific elements based on name and then grab the predicate of delete. So that sets up our first scene import rule. So the second scene import rule is going to be a joining of meshes. And so in order to set up that next import rule, we're actually going to look for an attribute of path instead of name. And so what that's going to allow us to do is it gives us a little bit of flexibility, because typically if you're looking for a name, then it has to be, this hierarchy has to be exactly the same every single project that you were to use this profile. But if you look for just a path and you don't actually give it a specific name of an element within the hierarchy, it gives it a little bit more flexibility in that these layers can be named anything and you're still going to get the combining of meshes the way that you want. And so using this regex syntax, we can just use pipe.star, which is going to grab each layer and mesh them independently of each other with all of the children on that layer. So that is going to combine meshes by layer. Then the rest of our scene import rules are actually applying material. So in order to apply material, we're using the material assignment predicate, and then we are using the attribute of name with match regex of the name of that layer with an underscore combined. One thing to note that's very important is that these scene import rules are, they happen sequentially. And so your deleting of the cameras happens, and then your joining of the meshes happens, and then after that is when you're, applying the materials happen. And so when we are joining these meshes, actually, this happens to rename the object within hierarchy, and it adds on an underscore combined onto that that layer name. And so when we are looking for this specific name, it's actually going to be altered to a-glaze underscore combined. So this is going to be correct, a correct naming convention. Then we are just going to create this new material, and we're going to feed it the previous material name that it is going to override. And then we're just going to set up the material how we would like. And so I have set up the application of several materials here with a few different new materials just based on color. And this is really just giving us the flexibility of changing it later within Game Engine if we would like. So these scene import rules are all set up. After these happen, then we jump to our mesh operations. Our mesh operations, we have a few different setup here. We are fixing normals, we are unwrapping our UVs, and then we're actually doing the mesh optimization itself. So we can look at these different setups here. Our fixing of normals is very simple, actually. This is just recalculating normals here within our mesh toolkit tab. Our UV unwrap is using a hard surface axial algorithm with a scale of 100, is something that I've found is appropriate for about this scale of model. And then our mesh operation, our mesh optimization here is we're just decreasing the polygon count by 90%. So we only want 10% of the original polygons. So once we run that, we are going to decrease our draw calls substantially, and hopefully we should have many less polygons than this original 277,000. So you'll notice that I had imported this model here, and we did not do any of the operations on this model yet. So I'm actually going to open a new scene here and bring in this same model, but I'm going to execute these operations. So I'm going to execute these operations. So this is actually only going to execute the scene import rules, and then I'm going to execute the mesh operation separately. Great, so this import happened. You will notice that within the outliner, within our hierarchy, as I mentioned, all of the objects got renamed with an underscore combined, and you'll notice that the hierarchy changed. So now all of these layers got combined, all the meshes within these layers got combined into a single mesh. You'll notice that our draw calls went from about 1300 down to 22, and our polygons actually went up a little bit.
So at this point, it's worth mentioning that inside of InstaLOD's viewport, we have a feature called real-time occlusion culling, which basically hides unseen parts for that specific frame. That is why, in this case, we're actually not getting the full polygonal count displayed on the top left-hand side, which for this entire floor actually contains 1 million polygons. So you'll be able to see that when we do optimize down to 10%, we're going to end up correctly with 100,000 faces.
But our mesh optimization has not happened yet. So I'm going to start this mesh optimization. Great, so this mesh optimization just finished, and it decreased the polygon count to 104,000 and 22 draw calls. All of our meshes are combined, and we are ready to export this as an FBX. So what's great is that now that we have this profile set up, save profile, it is just this JSON file that we can now use within InstaLOD pipeline over multiple models at one time. And this all happens in the background without this InstaLOD Studio client running, so this mesh optimization happens much, much faster and scales very nicely. So now that we have this profile set up how we like, we can use it on multiple models at once using InstaLOD pipeline. And so how to do that is we can just go to File, Run Profile in InstaLOD pipeline. And there's a few inputs here. You have to point this path to where you have the InstaLOD pipeline software. So this is actually, this dialog is a completely separate application from InstaLOD Studio XL itself. So then you have to supply it with a batch name, an output path for where you want to find these optimized models, as well as a naming format, and then you need to feed it the models that you would like optimized. And so I'm going to run this right here, and I actually have already ran this, and I have my output files finished, and so I will show you that right now. And here they are. These are our optimized meshes. You can see how small they are, and they are ready to be imported into Unity. So now that we have our sections of this tower optimized into FBXs that can be used within Game Engine, we're actually going to jump back out to Revit, and we're going to grab the entire shell of this tower that we're going to export out of here so that we can optimize within InstaLOD and use within Unity to build our AR app. So I'm going to use the same format that we have previously used, and we're going to export a DWG. Okay, so in this video, we are going to look at the entire tower shell model. We are going to want to optimize this down from 4.3 million polys so that we can get it into augmented reality. First thing I'm going to do is delete out these cameras, and then I'm just actually going to run a very straightforward optimization on this. So I'll create a new profile, and I just want to reduce this down to 10% of the triangles that it currently has, and I will run this optimization. Now we can see that this shell model has been reduced down to 340,000 polygons, and it's still retaining all of the necessary detail of the exterior ornamentation. So now we can export this back out to an FBX, and it should be usable within a mobile augmented reality application. I also wanted to show another model that I had just previously ran through InstaLOD is the tower slabs and structure model here. I have joined all these meshes and optimized them and brought them into Rhino here, which is equaling a total of 15,000 polygons. So it's very, very light. So we're actually going to overlay the shell model that we had just optimized on top of this core slabs and structure model, so that we can get, you know, a very detailed, robust model that we can then go and bring on site to get kind of an accurate representation of what this building will look like within its context within the city. Okay, so now we are in Unity, and we have compiled all of the models together into one tower. So we have the core slabs and structure model, as well as this shell model here that we optimized using InstaLOD, as well as this podium model. So this all came together very nicely with some reflective glass, etc. So now we are going to build this out into a mobile augmented reality application and try and bring it on site and see what we get. Awesome. So now that we know that our on-site AR tower application is running smoothly, we're going to jump back and start working with these section models. So I just imported these 4 sections of this tower into Unity here. You can see how the same optimization was done on all 4. With using that single profile. So you could see how you could use that same profile on all 80 floors at once and get the same great result. And also what's very valuable is that you know that all of these materials are the same. So if you were to edit one of these materials, it is dynamic over all of these models. So we are going to now build out an application that is going to use these different floor sections and see what we get.